Today we are going to be looking at the periodic table and the different patterns that can be observed across the rows and the columns of the elements. We've looked at some of these different patterns already, looking at the atomic number and at electron configurations. So we're going to continue this discussion and get a little bit more specific, looking at the arrangement, groups, periods, and reactivity. So let's start with arrangement. The periodic table is arranged by increasing atomic number. And if you remember, the atomic number relates to the number of protons in each element. And this arrangement is credited to Henry Moseley, scientist who organized his elements by protons, or the atomic number. But he is not considered the father of the periodic table. That's a different scientist named Dmitri Mendeleev. And the reason that Dmitri Mendeleev is given the title of the father of the periodic table isn't because his periodic table was the first one or even the best one, but because he figured out how to use the table as a tool for predictions. So he was able to figure out, based on gaps in his periodic table, what elements would be discovered in the future, where they would be located on the periodic table, and what properties they would have. And he was proven to be correct in time with those particular elements that he predicted. One of them is gallium. So Dmitri Mendeleev predicted the properties, location, and identity of several elements, and that's why he is given the title father of the periodic table. Another distinction of the arrangement we are going to look at today is based on the type of element. We have 3 element types: metals, nonmetals, and then kind of an intermediate metalloids. On the periodic table, you will find all of the metals to the left, all of the nonmetals to the right, and then separating the two, you will find the metalloids, which separate the p block by this kind of zigzag stair-step line. And those metalloids share properties of both the metals and the nonmetals. Next, we're going to look at groups and periods. Groups are the vertical columns on the periodic table, and periods are the horizontal rows. Each of them represent a different property for the elements in that column or row. So first, vertical columns. There are 18 columns on the periodic table, and in each column, those elements have the same number of valence electrons. We've looked at this already when we were talking about electron configurations, that our valence electrons match the A numbering of the groups, 1A through 8A, showing the number of valence electrons. When we have the same number of valence electrons, this leads to similar properties, because properties and reactivity relate to the number of valence electrons. We also give these groups family names because they are related by their number of valence electrons. And we are going to discuss 4 different family names today in a moment. But for now, let's just circle a group so you can see what I'm talking about. A column, there's a group, and this one in particular is named the alkaline earth metals, and it has 2 valence electrons. Periods are the horizontal rows. There are 7, just like there's 7 class periods in a school day. There are 7 periods or rows on the periodic table. And these rows represent the energy level of the valence electrons. So in a given row or period, all of the electrons of those elements are being added into the same period or energy level of the atom. with the exception of the D and the F block. Remember, the D and F block are 1 or 2 less than the row number for its energy level that's being filled. But the S and the P in this fourth row or fourth period, they are entering into that energy level of the valence electrons, which would be the fourth energy level in this row. The D block, however, would be going into the third energy level. If you're a visual person, I'm going to draw a picture to help you visualize what we're talking about. So in an atom, you've got your nucleus, and then our first energy level, remember this can hold 2 electrons. That's representing our first row of elements. Then we add another energy level. Let's do it as a dotted line. And then this is now representing our second row of elements, adding in those electrons. And it can hold up to 8. Third ring, the third period. Again, it can hold up to 8 electrons in that. 2 representing the S electrons and 6 representing the P electrons. Going on, it always holds 8 valence electrons from that S and P orbitals. Now let's take a look at reactivity using kind of what we've talked about with groups and periods for the valence electrons. Reactivity is a result of atoms trying to follow the octet rule. And remember, the octet rule means that atoms are trying to fill their outermost energy level to become stable. So reactivity is a result of atoms trying to follow the octet rule. Which is to fill the outer energy level to be stable. So you want that energy level in the outermost to be full, and to be full, all of our energy levels need 8 valence electrons. I'm going to shorten that to VE. Except for the first energy level, they only need 2 valence electrons to be stable, to follow that octet rule. So that asks the question, what happens if we have 8 valence electrons? Well, there is a group that has 8 valence electrons. That's group 18. They are called the noble gases. And this group is stable because they already have a full valence shell. That means they will not react. They are what we call inert. The ones that are really, really, really close to getting a full shell or following that octet rule are going to be super reactive. You probably already guessed it, the group 17 that has 7 valence electrons is the most reactive nonmetals. And the other group that is very reactive is group 1. You might be thinking, well, why? It has to gain 7 electrons to get to a full shell. You would be correct if the only way we can get to a full shell is by gaining electrons, but we can also lose electrons. And metals tend to lose electrons, and this is why. If you look at the Bohr model that I just drew, this has 1 valence electron. If I lose this electron, now I have a full shell in the previous energy level. So that would also be a way to have an atom following the octet rule. So group 17 is the most reactive nonmetal group. Group 1 is the most reactive metal group, since they are the closest to having an octet. Down in the example, you'll find a list of our group names and some properties. Let's recap what we've discussed so far. I've mentioned all of these names except for our transition and intertransition metals during our notes so far. So let's go back and recap them, and then we'll color code them in the periodic table provided. So if you want to grab some highlighters or colored pencils, I'm going to highlight each of these groups. You can do that with me. Alkali metals, that's group 1. They have 1 valence electron and they are the most reactive. So I'm going to color this, my highlighter here, and you'll notice that I am not including hydrogen, which is in that first column. And the reason is because it is not a metal. Hydrogen is a nonmetal, but it has 1 valence electron, which is why it's located in that first column, but it is not part of this group. The alkaline earth metals are all of the metals in group 2. They have 2 valence electrons. They are reactive because they can lose their 2 electrons to become stable, but not quite as reactive as the alkali metals that are very aggressive to get that electron out of there. We're going to jump over to halogens. Now we're in the non-metal side. This is group 17 or group 7A, whichever name you like to use for the numbering. And noble gases, that's group 18. These are stable and do not react because they already have 8 valence electrons. So halogens and noble gases. The other 2 groups represent the D block and the F block. Now we have names to give them. So the transition metals are all of the metals in that D block. They're the largest group of elements on the periodic table, and I'm going to color those pink. So all of these in the D block are my transition metals. And lastly, all of my elements in the F block are called the inner transition metals. The reason for this, if you remember, is that the F block fits right in after the S block of the 6th and 7th period, and the periodic table would push out and extend, putting the F block right there inside of the periodic table after the S block. So they are the inner transition metals. I'm going to color these purple. There's my inner transition metals of the F block. One more quick note about the F block. The F block top row starts with the element lanthanum. So this whole first row is called the lanthanides, and the second row starts with actinium, and this second row then is called the actinides. All of the lanthanides are radioactive and they simultaneously go through decay, whereas the actinides are man-made, or sometimes we call that synthetic. All of the elements that are not colored in right now, they are considered either other nonmetals or other metals, depending on if they fall to the left or to the right of our stair-step line, and all of the things touching the stair-step line are metalloids.